1, 2, 3, prova. Ma non serve, infatti non serve. Poi mi agito, sì. Poi inizio a alzare la voce.
Che non so bene per...
Quando uno è troppo felice, vedi? Ma qui sta registrando di già? Sta già registrando? Ah, questo
che poi è
registra continuamente.
acceso.
Ah, boh.
Ok.
Va bene. Ok. Qui abbiamo i gessetti colorati anche. Molto belli. Belli, belli. Gessetti. Sì, ovviamente. Chi se no? Ok. Ok. Okay, welcome back everybody. I think we can start. Okay, so yesterday was easy, right? It was very easy. Imagine if we started the first day with that. Would have been fun. Okay, so let's do a quick recap of yesterday, just to make sure that we've understood what, at least the key points. Okay? So yesterday, we started, remember, by looking at the gamma ray sky. And we say that, there is the galactic plane, which is very bright. There were all the resolved astrophysical sources. But we don't want that. We don't care about that. We want to remove them. And once we remove them, we remain with the unresolved gamma ray background. Okay? And one interesting property about the unresolved gamma ray background is that it's anisotropic. And that's interesting from a dark matter perspective because we expect the dark matter signals to also be anisotropic. And so the idea is that we want to understand if there is a correlation between the anisotropies that we do observe in the gamma ray sky and the anisotropies that we do expect from dark matter. And the way we do it is with the cross-correlation technique. And so what we did yesterday is that we started by defining the intensity of a generic field, the intensity fluctuations. Then we decompose the intensity fluctuations in spherical harmonics, so with the coefficients ALM. And then the angular power spectrum is defined as 1 over 2L plus 1, and then you have the ensemble average of these coefficients. Okay? Very good. So the physical meaning of the angular power spectrum is that it measures the correlation between intensity fluctuations of the two signals I and j that we want to correlate. If I equal j, autocorrelation. If I is different from j, is cross-correlation. Okay? Good. And then we use the properties of the spherical harmonics and the Bessel function to derive a more convenient form for the angular power spectrum. And so at the end of the lesson, we brought this. So we brought the angular power spectrum basically as an integral over the radial cumulative distance of the two window function associated to the two signal times the Fourier power spectrum. Remember, that's where we ended the lecture yesterday. Now, sometimes people, instead of using this definition, they actually use they multiply. So this is called the intensity angular power spectrum. Okay, or sometimes it's called dimensional angular power spectrum. Well, this is dimensionless. So usually here, like we want, this is the more like common, if you want, definition, okay? But it just multiplied by the intensity, the mean intensity. Just a preference if you want. Okay, so remember that we were discussing these steps, and what we were saying is that P of K quantifies basically the correlation between the 3D fluctuations. So this is a three-dimensional power spectrum, and it lives in Fourier space. It's P of K. Then we have the window function, which, if you remember, this is where you have the information on the source emission, right? In redshift. So how the sources are distributed in redshift, but it's also where you have part of the information about your instrument. Or better, imagine you have a survey, you know, they look at galaxies. Now you can't look with one survey at every single galaxy. Maybe there is some like redshift distribution related to your survey. So there is some information that is really like not just how much emission signal is emitted, but also like how much of it reach my detector. What's the observed one, okay, in redshift. And now we have the angular power spectrum, the CL. So the angular power spectrum measured the correlation between fluctuation, but this time it's 2D, right? Because we are integrating over redshift, which is basically an integration over the line of sight, if you prefer. And that makes sense because throughout all the course, we always say what we do observe is always a flux integrated along the line of sight. We don't see the 3D, we always measure like 2D, right? And that's what we're doing with the angular power spectrum. And the angular power spectrum measures so the 2D correlation in angular space. Cos theta is sort of like pi over L. So here, for the Xi, we were in real space. For the P of K, we are in Fourier space. For the angular power spectrum, we are in multiple space, or angular, if you prefer. And from this, we can see immediately that if we look at small l, then we are looking at large scales, okay? And when we look at large multiples, these correspond to small scales. Just when we interpret, at the end of the lecture, we will interpret the plot. It's something to keep in mind. Now, sometimes people like to plot, if you see like in papers in the literature, people sometimes plot this quantity, the L times L plus 1 CL over 2 pi. You see it all the time for like C and B. It just usually is visually better to plot it this way. But again, this is just a preference. It doesn't change the units. It doesn't change anything. Just like people usually do that in the literature. Now, plan for today. So we have this expression here, or the angular power spectrum, and we want to, so the window function, we have defined it yesterday. Remember when we wrote the intensity as an integral of the window function? Now we want to understand a convenient form for the power spectrum. And so what we do is that we start by looking at the so-called seed model. So this is the plan for today. Okay. We start by looking at the seed model, then we will connect it to the halo model, just to give, because the seed model, it's more of a, like, here we will have calculation. And then in the halo model, I will give you more of like a physical interpretation, if you want. And then we will extend it to the halo void model. And then at the end, I will show you also some window function. Okay? And then at the end, we will see some practical examples, so some interesting results, where we use all these quantities that we see today. Okay? Okay, so let's start with like the seed model. Okay, so a seed definition is any discrete object that sources the field you're studying. Okay? So now we're still, at this point, we're still generic. Practical example, if you're looking at halos, like in the halo model, your seed will be the dark matter halo. And the parameter, these dark matter halos are characterized by a parameter which is the halo mass. It's one practical example, of the seed model. Now, one important assumption of the seed model, so assumption, is that the observed field is generated by a population of discrete objects. Okay? These are the seeds that we just defined. And the second assumption is that the statistics of the field follow the spatial and mass distribution of these seeds. Okay? So what does this mean? What it means in practice is that the central assumption of the seed model is that if we have this is fx, so generic field, you can write it as a sum over A, and I will explain, f ma x minus xa, okay, where A is the seed. So we're summing over the seeds, okay, and we're saying that the total f, so my total field, is basically additive, right? So each seed contributes independently. And also each contribution depends only on two things. One are the intrinsic parameter ma. So ma can be any generic parameter. In the case of the halo model, this will be the actual mass of the halos, right? So it can be mass of the halo. In the case of the astrophysical sources, it will be the luminosity, because astrophysical sources are better characterized by their luminosity, and so on. But at this point, we're still generic, right? And then second, each contribution is also depends on the location. Because you see that there is the argument x minus xa. So that means that this profile is centered on the seed and is transition and invariant. So if I put the same seed elsewhere, this will produce the same profile. Okay? So if I have f ma x equal f ma x minus xa. Okay? So these things basically encodes the information of homogeneity. Cosmological principle, everything is homogeneous. Okay, and also say that there is no preferred location in space, so it just depends on the distance. Okay, so basically the so-called independent seed assumption can be summarized as f ma does not depend on the environment where it is and on other seeds. Okay? If you want to go beyond these assumptions, then you run simulations. But you can see that we can still do a lot of interesting physics with something that has these like assumptions, okay? Okay, so I told you MA are the properties of the seed, can be the halo mass, the luminosity, very good. Now, we define the mean seed density. Okay, now the mean seed density is defined this way, Mx is what we call dNdm. Okay, and the idea is that in the case of the halo model, what I call halos, this will be the halo mass function. So it will tell us how many halos, the number density of halos per unit of mass. In the case of astrophysical sources, this will be the luminosity function. And we will repeat this over the lesson, but it just good to keep in mind as like practical example, okay? So this is the ensemble average. The luminosity function, which is the number density of astrophysical sources per luminosity, because we said before, in the case of halos, that depends on the mass. In the case of astrophysical sources, the independent parameters are the luminosity, okay? Okay, now we can rewrite. We know that we can always rewrite. Let me see, where should I delete? I delete this one. No, I delete this one.
If I may go to
Go for it. Yeah.
So when you say like the seed model is like some object,
Yeah.
with sources of field, but it's like the dot matter field.
It can be. But like it's very generic at this point. So you can have, for example, the halos. So you have the dark matter field, and that's the source of your gamma ray signal.
Okay.
But you can have the astrophysical sources. At that point, you will have a luminosity, also gamma ray signal from the astrophysical sources. So at this point, we're being very generic.
Yeah,
But typically, the field is always the dark matter. Yes. Yeah, yeah. The underlying field is the dark matter.
and what do you mean by n over the mean seed density?
By what?
Is the derivative of n?
Oh, it's just like, it's like, no, it's, you know when you write like the number density per parameter, right? So it's just these. In practice, these will be for halos, it will be the actual mass. That's why in the seed model people use M, because then you understand immediately like the logic of it, because the seed model kind of started as a halo model for the halos. So yes, you can think of it in the interval, you know, what's the number of halos that have a mass between M and MdM.
Okay.
You can think of it this way.
And the n is not a subscript, right? It's a Cn on the left hand side.
Where
On the left hand side?
there is no, this is ensemble average. Okay. Okay, now you know that we can always rewrite. Let me delete first. Now we can always write a discrete mass as an integral of the of delta, Dirac delta, right? You can always write this x prime minus xa 1. And so now that means that we can write now that expression there at the top. We can always write it as fx. And now we have, instead of having the sum over the seeds, we have the integral over dm, our parameters, aka halo mass in the case of the halos and halo model, d3x prime. And then we have the sum of delta function. And now you will see soon why am I doing that. Because I want to use an interesting property. Okay, now we can describe the seed number density. So at this point, we leave it this way, okay? Now we can define the seed number density as the sum over A of delta function So if we integrate this in volume, we get the total number of seeds. If you want a practical example from real life, if I'm counting galaxy, each one of these elements will give me one. One galaxy, two galaxies, three galaxies. So that's why we have just delta function. I'm just counting galaxies. So at this point, dn dm, which I've defined there as ensemble average, this can be written as, so ensemble average of this quantity, right? So ensemble average of x minus xa, delta m minus ma, okay? But now we know that we can write f as can we write as dm d3x prime dn dm f. So this is a weight. Okay? It's here. Right? So this is now a convenient expression. Because now we have this that operates as a weight. Okay? So at this point,
I'm sorry,
yeah.
I don't understand how like the derivative like this. You take derivative of the number density n and it's average. But there is nothing average here, it's just delta functions. So why you
No, it's more like, you know when you consider like probability that you have like certain that depends on certain parameter? No, when you have like a function that depends on, I don't know, x given certain parameter, if you want, you should think of it this way.
okay.
If you want. Yeah, it's conditional, sort of like a conditional probability. You can think of it this way if it's
But
easier.
there are no integration involved.
I mean, there will be integral on the halo mass at the end. Yes, so this depends on the mass somehow,
Okay.
right? Okay, so at this point we have that yesterday when we defined the 2-point correlation function, we defined it as f, I'll write f1, f2, but if you prefer we can have f1, fi as fj, it's the same, okay? And so now we can write f1 as the integral over dm1 d3 x1 dn dm1, okay? And the same for f2, right? But now we have all the two. And here, actually, let me write it explicitly. Because here I will have dm2, d3x2, dn dm2, and here I have m2, let's put y minus x2. Okay, so at this point, what I wanted to show you, at this point, we want to write this expression here in a better way. Because if we substitute, let me see, let me write it explicitly so that maybe it's more clear. If I substitute now these two here, what I have is that xi, xy is, and I have all these integrals, right? So this will be an integral in mass 1, or like in parameter 1 if we want to be generic, mass if we want to apply to halos. And then you have integrals in m1, integral in m2, integral in the 3x1, d3x2. Now we have the ensemble average, and we have the sum over, what is it? Delta 3x1 minus xa. That comes from, we wrote it somewhere. Here we have the sum, right? So I should have put it here. And then we have the sum of B of delta 3 x2 minus xb, close ensemble average, f1 m1 x minus x1, and then we have f2 m2 y minus x2. So I have this quantity here that depends on the sum over A and B. And now I want to write it in a better way, because I don't like that sum. So I want to massage that sum somehow. So what I want to do is that now we separate the contribution. Because now I have a sum over A and a sum over B. And I say, okay, let's write this sum as the case in which A is different from B, and the case in which A is equal B. Okay? So we start by the case in which A equal B. This is like a short noise term. And this is due to the fact that we're working with like discrete objects. Okay? So at this point, if we write here, we have, let me see. Okay, so if we write this, we have delta 3 x1 minus xa, delta m1 minus ma, same thing for the others, delta m2 minus ma. And now we use a property, so this is what we want, okay? And now we use a property of the delta function. So I will complete this after, okay? A property of the delta function, then we have the delta x1 minus xa, delta 3 x2 minus xa. So we have the same xa, we have different x1 and x2. And this is delta 3 x1 minus x2, delta 3 x1 minus xa. So this is a property of the delta function. Same with if we put m1, ma. Same thing. So at this point, we can write these in a more convenient form. Because now we can write, let me go here. We can write this expression as delta 3 x1 minus x2, delta m1 minus m2, right? And then we have the sum over delta 3 x1 minus xa in the ensemble average, right? And then we have delta m1 minus ma. All I'm doing at this point is that I'm bringing outside of the ensemble average what does not depend on A, which is totally fine. But this is interesting because now you can see that this is exactly the definition of the NDM. So now I compactify this expression. Now, in the case, okay, so this is for A equal B. So one of the term of the two sum, it's done. Okay, it's this term here, the NDM 1, okay, times this delta function. And I'll write it again later in the total contribution. Okay. Now we want to do the second term. So the second term is what if A is different from B. And here there's not much we can do, in the sense that in the case where A equal B, we can compactify, make it nice. In the case where A is different from B, what we can do is that we can remember what we said yesterday. So yesterday, when we were defining the two-point correlation function, you might remember that we defined it as an excess probability over like two fields being completely randomly distributed. So in that case, we were just considering, remember, two fields, like 2 points in two small volume separated by distance r. Now, in this case, we're being a bit more, we're adding one level of complexity, because now not only we have dv1, dv2, but now we're also considering parameter dm1, dm2. Okay? So the expression that we wrote yesterday is slightly more complicated, but what we have is that if we have one object in a volume dv1 with parameter dm1, with mass dm1, then we can write this probability as dn dm1, dm1, dv1, dn dm2, dm2, dv2, and then when 1 plus the 2-point correlation function. It's exactly what we did yesterday. But now we have the dependence on the 2 parameter. And yesterday you remember that we had n squared dv1, dv2. So it was just like a simpler expression, because we're considering like the practical example of galaxies. So in that case, n1 was equal to n2. Now we're saying this might be possibly 2 different objects. And now instead of having like just a number of objects, now we're doing dn1, dm1, dm1. But, you know, it's just like a mathematical trick at this point. Okay, so now we can say, so this is again just to give you a physical interpretation, a connection to physics of what we're doing. We can also just do all the, the math and interpret the results, but I think it's good to keep in mind, even during the steps, that there is some sort of connection to reality. Okay, so at this point, when we do, so at this point, we can say that dp12 is n1 and 2 with this thing here, okay? Where n1, you can just rewrite it this way, n1, ni if you want, is the integral in volume of this quantity. So you can think of it as the number of objects in a certain bin I. Okay? And so at this point, we can write this dp1 e2, okay, as the integral d3 xi prime, same thing. So I'm just substituting, I'm not doing anything crazy. Okay. Substituting the 2, dm prime 2, and then I have, well, here, okay, okay, yes, and now I have to put the second one, yes, okay, x2 prime, m prime 2, and then remember we're doing the case where a is different from b, and so at this point I put all the integral on one side, okay, and now in the ensemble average I have this quantity here, right? A different from B. And now we work in the small bin approximation. And the small bin approximation, this is simply dv1. This is simply dm1, right? dv2, dm2. And so that means that in the small bin approximation, I can write this quantity, I can write that n x1 m1, n x2 m2 can be written as, for A different from B, as n1 n2, A different from B, over dv1 dm1 dv2 dm2. Okay? Now, at the end of the day, all I want to do is that I want to write, okay, so I have an expression for the mass function. I want to write, see, these nx1 m1, nx2 m2 as, and this is the sort of things that we want to write, because now we're comparing. Did I delete it? We had an expression for P1, 2 before, so look on your notes. But now we can compare them, and we can see that at the end of the day, you have dm1, dm1, dn, dm2, and then you have 1 plus, because we wrote before that we can always write dp1, dp2 as 1 plus the 2-point correlation function, okay? That's the definition. That's what we said yesterday. So now I have x1, x2, and then I have m1, m2. Okay. So the important thing is the following. The important thing is that at this point, we can write, we can sum the two quantity. So the case in which you have A equal B and A different from B, and get an expression for the Fourier power spectrum. So I'm just about to copy these two now. Let me just make sure that there isn't anything else that I haven't told you. Okay. Because now what I want to do is that now I have the sum of B, and then the 2-point correlation function is dn dm1, dn dm2, 1 plus the 2-point correlation function, okay, plus dn dm1 and the delta function. That's the case where A equal B, right? That we just derived 5 minutes ago. Okay. So this is the 2-point correlation function of the seeds. But now we have the 2-point correlation function of the fields. It's a bit when you say f of x. The seeds are the x. The 2-point correlation function of the xi is the f. Okay, so this is a function of the fields, of the seeds. Okay. So this can be dm d3 x1, and then you have dnm f1 x minus x1 parameter m, f2 y minus x1 parameter m. This is the A equal B term. And then we have the other term, which is dm1, dm2, d3x1, d3x2, and then you have the other terms, right? Because now we have the f function, because we're not looking at the 2-point of the seeds anymore, we're looking at the 2-point of the f. So now we have the f function here, okay? And this is times xi of the seeds. This is like why there is the S here stands for 2-point correlation function of the seeds, just to distinguish from the one of the function, okay? And this depends on the parameter m1, m2, x1, x2. Okay, now we're not gonna go into perturbation theory or anything too crazy, but the idea, let me delete here. The idea is that for the 2-point correlation function of the seeds, what people typically do is that if you look at large scales, or like after inflation, you can say that these, the density fluctuations are very small, and the evolution of these fluctuations is governed by linear perturbation theory. Because we're looking at small fluctuations. Okay? And in linear perturbation theory, one can say that your density contrast, so your matter density fluctuation, grow with a factor that is called the linear growth factor. Okay? So so basically you have the linear correlation, so you have the 2-point correlation function, it is called the linear 2-point correlation function. This is the 2-point correlation function, the linear one, is related to the primordial, or if you prefer, the p-lin, so the linear power spectrum, but we know since yesterday that the two are connected and give the same information. This is related to the primordial power spectrum. And this is something that is related to inflationary models that we're not going to do today. But it's just good to know in general where these things come from. Okay? So we're not deriving this today, because in reality what you have to do is that you have to basically solve it numerically. So you basically take the density perturbations after inflation, you solve them numerically. There are analytical functions that people give you, but I think at this point people don't use them anymore, and people use the P linear, so this quantity here from CAMB or CLASS, which are two tools online where they do it properly, numerically.
Just to be sure, the term below the A equal to B, which is F2.
It's y minus, yeah. Where we are in the first one, where, no, because remember when we did the A equal B, we collapse in them, right? We use the properties of the delta function so that we can collapse x1 and x2 and bring them outside. And we remain with 1. Okay? Okay, so this is just to say that where this is coming from. That's why I'm not writing explicitly an expression of the linear power spectrum, because this is typically numerically solved. So you have like a function from online tools. Now, what's important to know and I will explain it later, I think in a more clear way. For now, just accept it, but later I will show a plot when I talk about the Halo model, is that we want to connect the matter density, because so far I'm just talking about matter density fluctuations. Right? I'm pretending in a sense to be generic, but as you were asking me before, in the end, the underlying field is always the matter density field, right? So we want to connect the matter density fields with the halos, so with the halo over density. And the function that does that is the bias. Now, for 5 minutes, just accept this, and I will explain this better in a moment with like an actual plot. But I want to get to the end of the calculation, okay? So at this point, basically what we can say is that the 2-point, one can show that the 2-point correlation function of the seeds can be written as the product of the bias, B or BI, BJ, or B1, B2, times the linear one, the one that we get from like inflationary models, okay? So you're going to substitute these somewhere when we wrote the Fourier power spectrum, so you have it in your notes. And so now you have one term in your notes with the case in which A equal B, and one term that is longer, which is the case in which A is different from B. So what you have in your notes is that you have the P, the power spectrum, because now we can Fourier transform everything, right? It's the same information. And you can write the Fourier power spectrum as the sum of two terms, the one halo and the two halo terms, okay? Now, the one halo term is the one where A equal B, the small one, where you have the P1Hij is the integral in M of dn dm, and then you have the two functions, because at this point we're working with the function, right, of the seeds. K given M, and P, so H is now two different terms, dn dm1, bi, the bias that we just wrote, and then there is the second parenthesis, dm2, dn dm2, bj, m2, fj, and then we have the linear power spectrum. Okay? There is fj. Yes. Thank you. Okay? Now, at this point it's math, and we get to like the expression of the equation. Now we're going to go to the halo model and give like a practical example that is more intuitive, just to give like a physical and easy physical interpretation, an intuitive interpretation of these lots of math calculations that we just did, okay? So now, see. Yeah, it's because it's the Fourier transform. We are in Fourier transform now, okay? Also here, yeah. We went from the two-point correlation function with Fourier transform, and we are on the P of k, which is what we want at the end of the day, right? Okay, so now let's give you more of a physical interpretation. Because we can see, so now we derived all this calculation, but we can actually derive the same idea just with our intuition. Okay, so let's look at the halo model. So this is, the halo model is like a useful formalism that you can use for spatial clustering. You want to study spatial clustering. And the idea is that if we look at like numerical simulations, or in general at our understanding of how the universe works, the idea is that we have initially very small fluctuations in our universe, and then there is the expansion of the universe, so these expand, right? Expand, until they reach a critical density. They reach a critical density, and at this point, these fluctuations collapses. And that's when a halo forms, okay? So the idea is that now we have my fluctuations that goes above a critical density, and I have my first small halo. And now I have like two small halos, and they can merge, right? And they will produce bigger halos. And these bigger halos can also merge and produce even bigger halos, and so on. And so yesterday somebody was telling me, what do you mean that the Dark-matter distribution is hierarchical? That's what I mean. So basically you end up with a hierarchical structure of the universe. Now, if we have to put these in one plot, what we're saying me compute this, but I will write this again because we're getting there. What we're saying is that if we look at the density fluctuations, these are the density fluctuations of matter in space. They will look something like this. So in space, we will have different matter fluctuations. They will go like, crazy. And then when they are above a certain threshold, these are the density fluctuations that collapse and produce halos. So this one, okay? So these are all becoming halos. But this is telling us that the halos do not trace the entire matter distribution, right? They only trace the peak of the matter distribution. And that's something that we need to correct for, in a sense. So the fact that the halos trace the peak of the density distribution, not the entire, it's what we mean when we say that halos are biased. Okay? Because the bias is the function that connects the two. So the bias is the function that connects the halo distribution with the matter density distribution. Where delta, let me remind you, this is rho matter minus the average. And this is the equivalent where you have the number of halos minus the average number of halos over the average number of halos. So this is the bias function. Okay? So the intuitive meaning of the bias function is that this is really the link between the matter distribution and the halo distribution. Now, let's think of some examples. Okay, these I will keep it because we need it after.
Sorry, what is written over there?
NM, number of mass, given mass. So it's the number of halos with like mass M. Okay? And this is the average number of halos. Because we're comparing the halo, like the matter density contrast, the matter fluctuations, with the halo corresponding one, okay? To say that this is not a 101. There is like the bias is sort of correcting, if you want, for that. For the fact that I'm only tracing the peak. So I'm being biased towards the peaks, right? So at this point, let's make some examples. Because so we've understood why halos are biased tracer of the matter distribution, okay? Because they trace the peak. Now, question, to see if you really guys understood it. Galaxies, are they biased or unbiased? Biased. Very good. Okay, now, check mark, very good. How about weak lensing? Is it biased or unbiased? Yeah, we're more shy on the weak lensing one. But yes, weak lensing is unbiased. Okay, while this is biased. Because galaxies, I need to form halos, I need to form galaxies. So they also trace the peak of the density perturbation, or the density field. But weak lensing is sensitive to anything, right? So it's sensitive to the entire matter distribution. So remember when, like yesterday, we were saying, oh, there are like differences among the different tracers. That's one example of a difference. Some tracers are biased and some tracers might be unbiased. Usually you're happy if the tracer is unbiased. You don't have to correct for it. But there are other good reasons. For example, galaxies, you're happy because you have like huge catalogs. So, you win and you lose in life. Okay, also when it comes to the bias, not everything has the same bias, right? Like some things are more biased than others. So for example, if you consider, now I'm just sketching it, but like if you consider the dark matter distribution or the neutral hydrogen distribution, you might expect a bias, this is like 1. I mean, the numbers doesn't really matter. That was painful. Yeah, the chalk on the blackboard can be painful. Okay, so what's important as again, an intuition to have in life is that technically the astrophysical sources tend to be more biased than dark matter or neutral hydrogen. And the reason for that is that astrophysical sources are point sources, while dark matter and H1 are extended distribution. They tend to be more extended at sources. And so they are a better tracer of the matter distribution because the matter distribution is more extended, right? So it makes sense that astrophysical sources tend to be more biased than extended emission. Okay, now the halo model is based on two main assumptions. And when I will explain to you the halo void model, we will relax them. Okay, so for now, we have two main assumptions. One assumption is that the entire mass in the universe resides inside halos. That's obviously it's not, the reality will be more complex, right? Because not every single dark matter particle will be in a halos, but that's like a reasonable assumption. They cluster, especially today. The more you wait, the more halos you form, and the more matter will be clustered. So that's one assumption. And the other assumption is that you can study the mass distribution at two levels. One is the mass distribution inside a single halo. And the second level is the, if you want, the spatial, more than the mass distribution, but more the spatial distribution, spatial or mass distribution of the halo themselves, of different halos. So the idea is that you can translate these two levels in two different functions. So if you look at the distribution inside the mass, so now you're focusing on one single halo. This depends on the density profile, right? So the density profile is telling me how matter is distributed inside the halo. And then I want to study the correlation among different halos, right? Because that's what we want to do. We want to correlate different points. And this depends on the halo mass function. This tells you what is the number of halos. It's dn dm, what we're using in the equations before. So now in the halo model, when we talk about halos, this is the number of halos per unit of mass and volume. So it's telling us how many halos, sort of like not just inside the halos, but how these halos are distributed in mass, different halos. Okay? So now you can translate these, and I've write it here. You can translate these two levels into two different correlations, because now you can say that I can study correlation between points that are inside one single halo, so small scales, right? And this is the one halo term. It's the correlation between points inside one single halo, or you can study the correlation between points that are in two distinct halos, and this will be the large scales. And this is more the two halos. It's more complicated than that. This is not exactly 101 as I'm telling you, but overall, this is sort of true. Okay? So the one halo term is more sensitive, tend to be more sensitive to the smaller structure, while the two halo terms tend to be more sensitive to the large scale structure. So you can think of it in this way, intuitively. Okay? Now, in practice, I can also write, okay, let me delete the one on top. So now we have the one halo and two halo depends on this f function. And now, depending on what we're considering, now we can be a bit more specific. Because now we have that if we consider, so we want to know what's the phase of this f function that we have to put in the power spectrum, okay? So if we're doing the dark matter decay, for example, we have that the tracer in this case, and we're looking at the F. Remember, the F is like the fluctuations of something. And that something, when we're looking at dark matter decay, would be the density field, right? In reality, it's the density fields over the average, because remember, we're always working with like density contrast. So we never look at the density field directly, we look at the density fluctuations. Okay. If we're looking at weak lensing, it's the same, because weak lensing is also basically the density field. If we look at galaxies, or like we can look at astrophysical sources first. Let's see. That is a bit more, depending on how much time I have, I can do the full calculation or not. We'll do it. Okay. So in the case of the astrophysical sources, so remember, when we're counting galaxies, we wrote ng as the sum of delta function, right? Because at the time, we were just counting galaxies. So I'm summing 1 galaxy, 2 galaxies, 3 galaxies, just a delta function. Now, if I look at astrophysical sources emitting gamma rays, I'm not counting galaxies. What I'm doing is that I want to know how much each galaxy contributes to the luminosity that I'm observing. So at this point, I'm looking at GS. I mean, this is just a name. And now each source contributes a certain luminosity. Okay, so now I have L1. Li is the different sources, astrophysical sources. Okay, so in galaxy count, in the case of galaxy count, the weight, window function is 1. Here I have that the weight is Li. But remember, that we say it and repeat 1,000 times, that here we are looking at fluctuations, okay? So we're looking at GS x minus GS average over GS average. So this is basically 1 over GS Li delta D minus 1. So in this case, the weight is Li over GS. Okay? And GS is, as we know, dl times the window function, like okay. In the case of luminosity, in the case of the astrophysical sources, we don't have the mass function, like in the case of halos, but we have the luminosity function, okay? Because astrophysical sources are better characterized by their luminosity. So, in the case of astrophysical sources, F is L over GS, okay? Because of that. In the case, no, I think that's good. Am I forgetting anything? No, well, in the case of, galaxy, if you want. Yeah, let's do galaxies too. F, in the case of galaxies, is the number of galaxies in each region of the dark matter halos over the average density of galaxies. And this is typically given, but I'm not going too much into the details, but something called the halo occupation distribution, where for each survey, people give you the number of central galaxies and the number of satellite galaxies inside the halos. But I'm not giving you too much details about it. You can believe me. Well, unless you want to, but okay. So now we have a very generic expression for the Fourier power spectrum. Now let's give 2 examples of how it's written in reality, like two practical examples, okay? So in the case P delta delta, for example, so let's look at autocorrelation first. So now we are correlating 2 gamma ray signals that come from decaying dark matter, okay? Now we will have that the 1 halo term will be the integral over the halo mass of the halo mass function times the nu squared, where nu is the Fourier transform of rho over rho average. So we just said. And it's nu squared because there we have Fi Fj, but in the autocorrelation I equal j. So now we have F squared, okay? The two halo terms, in the case of delta delta, is integral in mass of the halo mass function, and then we have the halo bias, nu, square, and then you have the linear power spectrum. Again, we have one parenthesis squared because we're doing the autocorrelation, so I equal j. So the two parentheses becomes one parenthesis of the same thing. Now, this is the case of autocorrelation for like decaying dark matter, for example, to gamma rays, but it could also be an example of a cross correlation. In the case you have dark matter decay signal and weak lensing, because that also goes with like delta. Okay? Now, let's look at an example of cross correlation, for instance. But I give you time to copy meanwhile, and this we skip for your own joy. For your big joy, for the sake of time. So let's do, for example, an example of cross correlation. And we can consider, for instance, galaxies and decaying dark matter. Okay? So in the case of galaxies and decaying dark matter, we're looking at P1 halo, galaxy delta. What? Yeah. And then we have, let's look at the generic formula. We have the integral over mass, we have the mass function, and now in the case of galaxies, F1 is n gal over n average gal. And in the case of decaying dark matter, we just have nu. And then we have the P2 halo gal delta. And now we keep the two parentheses because we're doing the cross correlation. The first one is the integral over mass of dn dm bias n gal over n gal. And then we have nu integral in mass dn dm integral no. So just realize when we do with the weak lensing, though, we don't have one bias, I think, because the weak lensing is not biased, so that's the difference. But so it's not exactly that one written as it is decaying dark matter, but it's like very similar in the case of weak lensing. Yeah, I have one nu here. Very good, thank you. And now I need a bias, and now we have a P-lin. Okay, that's a 2 halo. So these are two practical examples. Now you can see that once you've written this recipe, it's kind of very easy to go from one to another because you just have to think what is the Fi and what's the Fj. And that's it. So it's very versatile. So this technique is like, it's maybe hard to understand at first, but once you do, you can apply to any different kind of tracer, any different kind of signal. It's just a recipe. And if you have like develop in your code, for example, the galaxy as tracer, that part remains fixed, and you can put all possible gamma ray signal. You would just have to change Fj. F1 will remain fixed, and vice versa. Imagine that you have, like, in your code all the possible signals from dark matter. You want to change a tracer, you will just have to change basically the part that relates to the tracer. It's a nice way to separate, in a sense, the small and large scales, but also the contribution, the part that comes from the tracer, from the contribution that comes from the astrophysical sources of the dark matter. Okay? Now, in the last part, we'll see how this change when we go from the halos, so the halo model, to the halo void model. Okay? So now I will delete this one. Okay, so let's talk about cosmic voids first. Okay? Okay, what are cosmic voids? Cosmic voids are underdense regions in our universe. And it's just like a result, they naturally arise as a result of the large scale structure, right? Because gravity is attractive. And so the idea is that matter always, so if I have like a halo that is bigger, matter will always go towards the place with more matter, just because of gravity. So it means that as we wait in time, cosmic voids will remain emptier and emptier and will become larger and larger because matter is just moving more towards the halos. But the important thing is that cosmic voids are not empty. They're underdense, right? If you say that something is underweight, you don't mean that the weight is 0. Right? You mean that it's less than average. It's the same. They're not empty, they're underdense. And if you look at what's inside voids, the majority is actually dark matter. Okay? So they're like dark matter dominated structure. Now, a lot of the statistical properties of voids are kind of debated. This is like a very much of an active topic of research. People use different void finders. They also fight a lot over what is the best void finders, possibly, you know. And so some of the statistical properties are currently debated. There are some where there is a sort of general consensus. And these are, so let's see some properties of cosmic voids. So one is that on average, and I will emphasize, everything I'm going to say, it's on average. Okay? They have a density that is as low as 10-20% of the background matter density. So they're underdense. Second, on average, they are pretty spherical. Emphasis on average. There are some voids. If you look at individual voids, there are some that are like pancake voids or like all sorts of shape. And they tend to have diameters, so like sizes of like tens of megaparsecs. Some are even bigger, so they're giant. You can find, but again, on average, because you can also find small voids, and you can have like voids that are hundreds of megaparsecs, but on average, you can say it's like tens of megaparsecs. And then a third property is that matter from the interiors tends to accumulate towards the boundary. Remember when we were talking about the halos and the galactic center? We were saying, oh, the galactic center, there is like an overdensity. That's a halo, because it collapses. The voids is the opposite. And I will show you a plot later. So that means, and it also makes sense, because the more I approach the boundary of the void, the more I want to reach the background matter density, right? So it's intuitively, this is nothing crazy, right? Okay, so these are general properties of voids. Say again? So the idea, again, it's like on average, and some simulation might slightly disagree, but on average, you have that voids expand. And you have the matter is just taken out from everywhere and moving out. So it's just like they expand spherically. It's more like halos, they have like these triaxial sometimes that you might expect. You also have this kind of shape for individual voids. Like imagine if you have individual voids like bordering filaments, they might have a shape that is not exactly spherical. But if you look also in simulation, or you take the SDSS map and you just look at voids, you can see that it's kind of true that on average, they tend to be more spherical than halos. That's kind of, it's observation, it's like also from simulations. And we also kind of expect it from the wave, because it's like matter is going out, they tend to expand. Why would they expand the preferential in the direction, right? Okay, so now we go from the halo model to the halo void model. In the halo void model, same idea as before, density contrast, great, here you go. Remember, above a certain threshold you form a halo, but now instead of having a one barrier, where you have above, you form a halo, now you have a two barrier model. And you say that below this barrier you form a halo, you form a void, okay? So now you go from a one barrier model to a two void barrier model. If you want, there are even things that are more sophisticated, because you might ask what happens here. So there are models that are even more sophisticated. They are called the halo void dust model, where you have three components instead of two. So instead of saying matter is inside halos and voids, you say matter is inside halos, voids, and something else. But we're not doing that. Now we're just doing the halo void model, okay? For simplicity. And so that means that if halos do not trace the matter distribution, but they trace the peak, voids do the opposite. So voids are also biased, or if you want to be more precise, they're anti-biased, okay? Because they trace the underdensity. So now we're relaxing some of the assumption of the halo model. In particular, we're saying that matter can live inside halos, but it can also live inside voids. And so in practice, that translates into a proliferation of terms. Because now the power spectrum is going to be the one halo and two halo terms that we had before, which is the case in which you have correlation inside the one single halo and two different halos. But now you also have the one void and the two void terms, right? When you have correlation between points inside one single void or in two distinct voids. And in principle, you can also have the cross term, because you can correlate the points inside the voids and the points inside the halos. Why not? So now you have a proliferation of terms. If you have a halo bias for halos, now you have a void bias. Right? If you have a density profile inside the halos, like an FW, right? Now you have a density profile inside the void. And if you have a halo mass function that tells you how many halos of mass A you might expect, now you have the same for void. The only real difference here is that, remember when we say halos are better characterized by M, the mass, astro sources are better characterized by their luminosity, voids are better characterized by their size. Mass is not really a great parameter if you want to consider something that is underdense, but they're very big. So that typically their MA parameter are the size, the radius of the voids. Okay, now I'm not gonna show you all these functions, but there is one that I think is interesting. Yeah, I think we have time. There is one that is interesting, which is the void profile. So there is debate in the literature about what's the correct profile in voids. People fight. And there are two main proposals. One is the so-called Amaus, Sutter, and Wandel profile. So in this case, you have the density contrast inside voids as a function of R. R is the distance from the center of the voids over the size of the voids. Okay? So now let's take a void that is small, or like small average, 9 megaparsec. It would be something like that. This is 0. So this is the background matter density, okay? So this is a 9 megaparsec void. Now we take something that is a bit bigger. We have a 30 megaparsec void. And now we have a even bigger voids. We have like 70 megaparsec voids. 70 megaparsec. Okay, so let's look qualitatively at the behavior. So what we see here is that smaller voids tend to be more underdense in the central region. but they also show a compensation wall. While larger voids are the contrary, no? They are less underdense in the central region, but they have smaller or no compensation walls whatsoever. And then there is the second, so this is the Amau, Sutter, and Wonder profile. And then there is the Voivodich profile and friends. That is completely different behavior. Same axis. This is like matter density. This is 9 megaparsec radius. This is 30, this is 70. So you can see they all have sort of empty centers and no compensation walls. Now, asymptotically, they all tend, actually this is, wait. No, yeah, that's correct, because this is 0. Okay, asymptotically, they all tend to the background density. That's, it must be, otherwise it's wrong. But inside, what happens inside the void is very different. So I always say, the Mouse, Saturn, and Wonder profile, if you've been in Chicago, is like a Chicago pizza. Because the deep dish pizza, you have like a thick crust in the end, you know, at the boundary. That's sort of like the compensation wall in my mind. And this is more like an Italian one.
The Chicago pizza inside is not void at all.
But the difference is that it's very dense. It's the closest thing you know to a neutron star.
Yes.
Okay. And then...
I'm sorry, like, why do we have these two different ones? Why can't we just check our simulations?
Because simulation differs. So the idea is that some simulation, so the definition of voids is very different in different simulations. So some simulation define voids as empty spheres that expand, and then once you reach like 20% of the average density, you say that's it. Other simulation defines void geometrically. So you let your simulation evolve and you know where your filaments and clusters are, and then geometrically you see where a void is. And then there are some algorithms that defines voids dynamically. These are the DIVA algorithm, where they define voids as outflows of matter. So these are different assumptions. They all make sense. They're all like, they're not crazy, but they give very different solutions. And now we do have data. We have the EBOS catalog, which is fairly small, and as of a year and a half ago, say again.
Sorry, I understand that the void finding algorithms can vary in the definitions of the voids, but I don't understand why changing the void finder algorithm would lead to a difference in the density profile of the void. Because here we have different density profiles, right?
Yeah, these are density profiles. These are like different people that run different simulations, they're different algorithms. I think that it's also part is like the lack of data, but I'm also kind of like hesitant in saying that that's the only reason, because when you look at data, you also use the same algorithm on the data. So for example, the Amau, Saturn, and Wonder people, they say we match better the data because it seems that in the data there is this like compensation walls, but they use their algorithm. So one has to be like hesitant. The good news is that the cosmic void era is starting, right? Because now we have the DAISY catalog, which is like a year and a half ago. But now there are more DAISY data. LSST will see voids. Euclid will see voids. FEREX will see voids. So now Roman. So now there will be more data. And so maybe in 5 years from now, if I give these lectures, it might be different. And also, like, people are improving their simulation. They're kind of understanding better their properties. So this is sort of what people are debating today. 2 years from now, 5 years from now, might be very different. But I think most people right now use this one, by the way. This is the most known. But it's good to know that other people running different simulation got a different results. So this is sort of like state of the art in the literature.
So when it comes to the halo mass function, there is a standard model, right? We think it's mass function.
Yes.
Right?
But then there are also different models that people use, right?
But
like Shetty Torment.
right?
They're pretty similar. That is correct. Yeah. Yeah.
When it comes to voids, apparently there isn't, right?
They derive that too, which is like very similar to the Shetty Torment profile. So there is, but there is one paper on this subject, as far as I know. So that's why it's like you don't have like a lot of people working on this. They try with like a very similar formalism. Basically, what they did is that they take the Halo model and say, let's base on these and extend it to include also voids. but it's all like very new at this point. It's all like, yeah, sort of like the state of the art. This is where we are now. It's not like the other things that we discussed over the course. They're well understood. People have been doing for like decades. There is like a solid knowledge in the field. These ones, opposite of that. It's still like very much debated. Okay, so this is also sort of a thought-provoking, and it's also to give you like an idea of like sometimes in courses you see things and they seem like set in stones, but in real life things are not set in stone. Like people argue and people like get wildly different results, and in 10 years people will give a void talk and it will seem, oh, like the NFW profile. That's what everybody uses. But it takes decades of people arguing, and that's where we are now in the big argument.
So is there intuition why, for instance, the halo mass function has a standard profile but the voids don't? They seem like pretty similar things, right?
The halo mass function, I think, well, there is one paper. I think people are debating less about that. The only place where there is like a big debate is like the density profile. That's as far as I understand it. That's where people are like unsure. But the number of voids that you expect from simulation, you sort of count them, right? Like when you look at the halo mass function or the halo void function, we're counting how many halos of this mass do I see in my simulation.
So this is agreed upon.
Well, it's agree when you have one paper, who's agreeing with who, right? You need like, sure. Like there is I didn't see people getting angry about the void mass function.
But surely if you do one simulation, you can count the number of halos,
Yeah.
number of voids, right?
You can count them both. So at the end of the day, you have both of them, yes.
And people have been doing simulations for a while, right?
Yeah.
So, I mean, whenever people started doing the halo mass function, surely they also were doing the void and counting voids as well, right?
You can do that, yes. It just maybe what I mean is that in the halo mass function you have like a nice analytical formula, and that's, as far as I know, it's like in one paper. But sure, with every simulation you can do what you're saying, sure. And I think, as far as I know, there isn't like much debate against that. I think people agree on the number of. Oh, that's actually not even true. That's not even true, because like, no, I take it back, because like if you consider different simulations, like for example now, people say that the volume that you see in voids, certain people say 60%, other people say 90%, and also I think the number of voids that you see actually changes, because different simulations sometimes expect like thousands and thousands of voids, and other simulations expect way less or way more. So I think they're arguing on that too, actually, yeah. It's not that weird.
Why you would study void create visibility? Now,
Yeah.
it was not that interesting before. Now it's that resistant because most of the places you can do for Arcanas better than
Yeah.
So clusters are actually where galaxies are. That's where clusters of galaxies are, with halos. So that's what no one was studying before. Now people realize that void, since they are under dense, you can fit better the expansion of the difference. So void is now a tool, or will become a tool also to study.
I mean, the fact that something can, yeah, the fact that something can be done doesn't mean that something has been done. In the sense that voids, where people that look at voids, most of the void science, it will be for magnetic fields, because people that study primordial magnetic fields, they really want, that's a void is a great place to look at.
That I understand. I'm
Yeah.
just confused why, when you do a simulation,
Yeah.
people agree on the halo mass function, but you're saying they don't agree on the counting voids. That seems weird, right? Because if you do a simulation, I mean, they're like duals of each other, right? So if you agree on the number of halos, you should also agree on the number of voids.
I think like they don't agree on the number of voids. They haven't really checked. There aren't different papers comparing the halo mass function, as far as I know, the void mass function, as far as I know. But there might be some recent paper where they did that. I think part of the reason why people didn't check or cross-check that is because there isn't like super much interest until like recently. So I wouldn't be surprised if the next year there will be like more papers on that and people will start arguing on that too, maybe. So far, people have focused, as far as I know, on the void density profile. But to be checked.
This would be also sensitive to maybe things like feedback, because simulations do not agree on like magnetic
you have different simulations, but as I said, it's like I think people, they could check, and I've talked with some of the colleagues that are actually interested in using their simulation to check that, but as far as I know, they haven't yet. But yeah. Okay, so, which by the way, it's all good if you guys love simulation, that's like a paper. So you should all think about it this way. It's good when there is something that can be done and hasn't been done extensively, you know. Okay, cool. So now the next thing in the next 10 minutes. So for the window function, I will just show the plots because otherwise we'll go over time. So now we have the information that we need to build the Fourier power spectrum. Now for the window function, they are typically shown normalized to the Hubble parameter and the mean intensity. That's a window function, and we have, so the window function of, here I can use colors, maybe. Let's use colors.
Sorry, can I ask you just one?
Yeah, go for it.
Could you please write it bigger because
Oh, yeah.
it's fading and I cannot see.
Yeah, I can write it bigger.
Thank you.
Okay, so we have the window function of BLLAC is going to be something like this. Then you have the window function of flux spectrum. Let me see that I'm doing it well. The window function of flux spectrum radio quasar. Then a different color, you have the window function of star-forming galaxies, which is something like that. Remember, I mean, it's a sort of like that, okay? I mean, you can find the right papers, but remember when yesterday I think it was, I told you that star-forming galaxies are separated into 3 populations. Population number 1, population number 2, population number 3. Okay, we see them in infrared. And then we have misaligned AGN, which I do with the same, which is also sort of something like this. I mean, for what I want to say, it doesn't, it's fine, okay? I can show you the right plot if you're interested. What's important is that now we're comparing with the tracers. So let's say that we want to look at galaxies or weak lensing, right? If we have like a galaxy tracer like 2 mass, this will be more, this is more peak around redshift, I think it's 0.1, 0.2, so it's like lower redshift. This, let's say that is like 0.5, okay? So this is like something like 2 mass. So this is like a galaxy catalog that is skewed at low redshift. And now we can have Euclid with lensing, which is gonna be something like this. Euclid with lensing as an example. Euclid is taking data now. And then we have the one of dark matter. So the one of dark matter, well, let's use red, will be something like this. So it's very different because the astrophysical sources tend to have a peak between redshift, 0.5, usually the peak. It's around 0.5, so larger redshift. While dark matter tend to have a prominent peak at low redshift and then quickly decays. Most of the dark matter signals come from today, from the clustered halos today, okay? And also another reason is that we're looking at the unresolved sources. So if you have a blazar that is nearby, that one is most likely is resolved. So the blazar will be the one with the peak at the larger redshift because they are the brighter objects. Remember, we're looking at observed objects. While star-forming galaxies, which are very faint, or misaligned AGN, which, as we've said, we don't see them in gamma rays that much, they might contribute also like nearby because of their low luminosity. Okay, so this is like the qualitatively the physical explanation of it. So what we learn by looking at this is that in general, your signal is enhanced, your cross-correlation signal is enhanced when you have an overlap between window function. Okay, remember that in the CL you have W1, W2, window function of gamma rays from dark matter, window function of gravitational tracer. So that means that in general, if you have a tracer that focuses on low redshift, again, in general, there are 1,000 caveats to this assumption, but in general, it would be better if you want to probe dark matter. If instead you are an astrophysicist and you're interested in studying the unresolved astrophysical population, then you might want something that overlaps better with your astrophysical sources. Again, with 1,000 caveats to this statement. Oh, this is the Hubble parameter and mean intensity. Yeah, the reason they do that is that this way you bring them more or less at the same level, because in reality, BLLAC tend to be like brighter and star forming galaxies tend to be lower, so you want just to, it's a normalization to have everything on the same plot. But okay. So now, in the next 5 minutes, we can sketch some interesting results and why cosmic voids are interesting for dark matter, okay? So we had the Fourier spectrum, we have the window functions, at least an intuition of them. And now we can actually look at how the cross-correlation signal look like. So we look at the angular power spectrum. And there are like 3 lessons that we can learn by looking at that. The first lesson is that, let's consider, what model are we considering? Let's consider dark matter that annihilate or decay into BB bar, right? And these BB bars do magic, and magic usually is pions. And they give us gamma rays. And for a moment, we forget about the astrophysical sources. Okay, we're just focusing on comparing annihilating and decaying dark matter. Okay, so we have the mass. The mass is like 100 GeV, and the cross section is the thermal cross section, so standard for a WIMP. Remember, we saw it Wednesday, I think. And in the case of decay lifetime, then we can consider something of this sort. Okay. So now we have the angular power spectrum here. I'm looking at the dimensional one, so if you're interested about that. But again, let's focus on the important details here. So now I'm going to tell you, this is the multiple, okay? Ciel, multiple. So if I look at the signal that I expect from annihilating dark matter inside halos, I expect something that is 10 to the minus 14. If I look at decaying dark matter inside halos, I have something that for that specific decay lifetime is 10 to the minus 15, but I can always play with the normalization, so it doesn't matter. What we care about is the relative difference, okay? If I look at the signal from decaying dark matter in voids, I'm more or less at the same, similar, not super similar level, I will tell you in a moment. And then I look at the signal from annihilating in voids. And here we are at 10 to the minus 20. So if you want, let's look at the relative difference. So you can see that the signal from halos annihilating dark matter tend to be bigger in general from halos, which is expected, because halos are over density. So you do expect that the signal is larger in halos than voids. The question is by how much? So if we look at CLH minus CLV, CLV, L, and here you have 10 to the 5 for annihilating dark matter, and then you have something of, here is 10 to the second. So what this, again, it's a sketch, I can show you the correct plot if you're interested, but what you can see is that when you look at the difference between the signal that you expect from annihilating dark matter in halos or voids, for the case of annihilating dark matter, there are 5 orders of magnitude of difference. So you do not look for annihilating dark matter inside voids, which makes sense. They're under density. In a halos, the probability of 2 particles annihilating is large. In a void, the probability that 2 particles scattered in this large volume interact is much lower. Not crazy, it's kind of intuitive. Decaying dark matter is still lower because I have less matter, but it's lower by a factor that is between 50 and 100. So I'm losing power. I'm losing a factor 50 and 100. From now on, I will focus on decaying dark matter. But at this point, so the lesson number 1 is that if you want to do dark matter research in voids, you better focus on decaying dark matter. But at this point, why should I do it? Right? Like, why I'm losing like 2 orders of magnitude, like almost 2 orders of magnitude. Why should I do it? And this is when the second lesson is important. Because now we remember that we have astrophysical sources, right? So we remember that we have astrophysical sources. And now what we do is that we look at the ratio between the two. So now we have the CL that we expect for dark matter over the CL that we expect from astrophysical sources as a function this time of the decay lifetime. Okay? In the case of, so this is 1, so this is where the astrophysical signal is at the same level of the dark matter signal for that kind of candidate, standard WIMP. Okay? So if we look inside halos, we have something of this type. So this is like inside halos. So we can see that most of the time we're always astrophysically dominated. Consider that here is where we have the current lifetime bounds. So we want to be here because this is kind of already excluded. We already know that that candidate is dead. If we look inside voids, this is where we stand. So in this case, it's like 10 to the 4. Well, okay, the signal can be 4 orders of magnitude, but again, this is like a less interesting region. It's actually more like that, sorry. And it's at the same level of the astrophysical background, around 10 to the 30 seconds. So 3 orders of magnitude above the current limit on the lifetime. So what's interesting about cosmic voids, like compared to halos, it's that this is basically a background-free environment. Like your astrophysical sources somehow, like they're less important than your dark matter signal. And every time you do indirect detection with cosmic void, in general with like astrophysical probes, you want to choose places where your astrophysical background is low, because that's your enemy and that's your problem, right? Now the last plot that I will show you are, and we have 5 minutes. Now we'll show you 4 different plots actually. So we have CL, so this is a standard angular power spectrum, okay? CL, and now we'll tell you which one, what it is. CL, CL. Okay, so on this side, we have the one from halos. These two are the one from halos. These one are the one from voids, okay? The upper one is, if I consider like galaxy catalog, where usually the cross-correlation signal with galaxies is like larger than the cross-correlation signal with weak lensing. And below is weak lensing, okay? This is how I separated the blackboard. Okay, so the total signal expected with the model that we currently have, because this is like theory at this point, we're not using data, okay? It's like theory. The total signal for the cross correlation inside halos with like galaxy catalog, a galaxy catalog like to mass, we have the dark matter signal is more or less at the same level of star-forming galaxies misaligned GN, and then you have the blazars that are lower. Blazars, flux spectrum ratio quasar is even lower. This is 10 to the minus 11. This is 10 to the minus 14. Let me do all the plot and then I discuss. Okay. This is 10 to the minus, okay? Okay, and the last one is you have BLLAC, and then you have other stuff below that we don't care. Okay, minus 15, and this you have minus 19. Okay, so the good point of the cross-correlation technique is that by using the cross-correlation inside halos, we have a signal where the dark matter contribution and the contribution from the astrophysical background is basically the same level. Why? Because you're playing the game of the window function. In fact, you can see that if you compare galaxies and like weak lensing, where you have like the different window function, you see that if you just forget about dark matter for a moment, in the case where we focus on low redshift, the cross-correlation signal from astrophysical sources wins, is like the one that wins are star-forming galaxies and misaligned GN. Where you look at the window function that is more at higher redshift, who wins are BLLAC. Okay, this is due to the overlap of the window functions. Now, what's interesting is that when you look at autocorrelation or like intensity, you expect your signal to be much lower, while with the cross-correlation, you manage to bring it at the same level of your astrophysical background. Now, you might say this is great, because now we have a statistical tool that somehow leverage on this different redshift dependence and put my enemy at the same level of my hero. But the problem is that even if that was the case, you cannot make any strong claim about dark matter detection in this scenario, because we don't know these astrophysical models perfectly. There are like uncertainty, and so even if you observe a signal, let's say that your data are here, and you say, oh, that's exactly what I expect, you can always explain this just by changing a bit your luminosity function of like your astrophysical model. And you can make it without dark matter, unfortunately. So you can make like a strong claim in favor of a dark matter interpretation by looking here, even in this like optimistic case, an optimistic scenario. Okay, now if we look inside cosmic voids instead, what you expect is that you have a signal that is expected to be orders of magnitude above your astrophysical backgrounds. In the case of weak lensing, even like 4 orders of magnitude, 2 orders of magnitude, so 7 orders of magnitude. So if you do observe a signal like that, that is a strong indication in favor of a dark matter interpretation of the signal. Now the problem is that this signal is very small. So there is no detector that we have today that would ever be able to observe such a signal now. We need something better. So right now, the best thing that we have is like Fermi. We need something that is like bigger and better, but it's not that far from, like people are already thinking of next generation gamma ray detector, like APT, the astroparticle telescope, that in principle would have the capability of observing such a signal, but you know, it's in the future. So the point is that this is like one example. It has just been done for like WIMPs, but in principle you can apply to any kind of like decaying dark matter, like pick your favorite model. This is with gamma rays. You can see what happens if you consider infra and so on. But this is what makes cosmic voids kind of an interesting place to look at for dark matter. There are lots of uncertainty still, so people are like very much talking about it. It's exciting that there are so many data, so that will mean that we will know more about these structures, and we will learn a lot of physics about it. So yeah, I mean, this was the last thing that I wanted to tell you. During this course, we have, I really wanted to emphasize the connection between theoretical physics, astrophysics, cosmology, using observation simulations like models together, and I hope that you enjoy it. Have lunch.